Hi guys, it's Kate, and this is the second video for week 1 of Math 23B. In this video, we're just going to take a look at an overview of what we're going to be studying this semester. We're going to be starting off by talking about integration. Obviously, we already started discussing that a little bit. We're going to get into exactly how to calculate integrals by converting them to iterated integrals. Iterated integrals are when you have multiple integrals, say double integrals or triple integrals, where instead of evaluating an integral over an interval, you're evaluating it over a region in the plane, that's a double integral, or evaluating it over a region in space, that's a triple integral. And so there's an order to the variables that you'll be integrating with respect to. Perhaps you'll be integrating with respect to x first and then y. Or perhaps you'll be integrating with respect to y first and then x, in which case you would swap the order of these guys right here. Note that you sort of read the dx and the dy from inside to outside. This integration sign and this d variable is what is paired together, and this outside integration sign in this variable is what's paired together. So we start from the inside and work our way out, but we'll get to more of that when we're actually doing iterated integrals. So we'll start with that, learning Fubini's theorem, again something we'll get to in due time, and then we'll also talk a little bit about numerical approximation, or what happens when you're unable to compute antiderivatives of particular functions. Similar to left hand, right hand, trapezoid, midpoint. We're going to talk about all of those and then talk about their various error bounds, which ones are the most accurate and why. We're then going to start integrating over, like I said, not just intervals, but regions in the plane, regions in space, and so you might already have guessed that we'll be integrating over manifolds, which we were introduced to at the end of 23A. We're going to have to figure out how exactly to describe these manifolds, though. You can't just say, integrate over this sphere. How do you mathematically describe a sphere so that you can integrate over it? And we already talked about parametrizations a little bit at the end of 23A as well, but what we're going to be doing is exploring the power of parametrizations in much more detail. So we'll be integrating over manifolds, and what the parametrization does is it takes every single dyadic cube that you see in sort of terms of x, y, and z, and it turns it into a little parallelepiped. We're going to get into this in much more detail, but a parallelepiped is basically a k-dimensional parallelogram, and whose volume can be computed by using determinants. And basically, since we're no longer working with parametrizations, we're no longer working in x and y and z necessarily, these cubes, these dyadic cubes, need to turn into maybe dyadic wedges or dyadic parallelepipeds in this case. And so this volume stretching and scaling factor is really important to take into consideration. We're also going to learn a couple of techniques of integration. So we're going to extend the univariate approach of integration by substitution to a multivariate approach using a change of variables formula, and talking about how, if we need to simplify a particular integrand or a particular region in space and describe it using a different set of variables, how to go about doing that. We're going to gradually make our way towards the fundamental theorem of calculus, but a generalized version, something that works not just in R, but works in Rn. And so one of the things that we have to do en route to that is that we need to define a couple of objects, specifically form fields, and we're going to talk about how these form fields can be integrated over oriented manifolds. So this is very challenging stuff. Orientation is very delicate. You'll be introduced to this in lecture. There is some notion of orientation in some calculations that we'll be doing, and so we'll be experimenting with when do we need orientation? In what settings have we seen it before? And so what we'll be doing here is we will take these form fields, integrate them over oriented manifolds, learn all about orientation, how to create parametrizations that preserve or reverse orientations, and then we'll be able to evaluate integrals of these by using these parametrizations. And then at the very end, after defining the oriented boundary of an oriented manifold, that is again a little challenging, takes a bit of practice, we can formulate this generalized version of the fundamental theorem of calculus, which is called Stokes' theorem. It is a really powerful theorem that connects a bunch of different topics, and depending on what applied field you may be going into, perhaps you've already seen a couple of these topics. The gradient, the curl, the divergence, all of these properties and structures come into play when you're dealing with Stokes' theorem, especially in lower dimensional spaces. But Stokes' theorem holds in Rn. So one of the most important things that we discover and work with extensively is this notion of the exterior derivative. And we'll be talking about that throughout the semester. You know, all these things don't really need explanation right now, but this is our general story. We're going to follow the line of integration in Rn. We're going to start with basic notions like the Riemann integral, which we've already talked about, and we're just going to build up its complexity and see how does it operate when you're outside of just the real number line, when you're dealing with some n-dimensional object that you're trying to integrate over. And what's the analogous version of the fundamental theorem of calculus that holds there? So that's how you should sort of follow the trajectory of what we'll be talking about this semester.